off this.
Do you want our cams on?
It's up to you, man.
Bro, it'll be like an awkward ass view. I'm just letting you know.
Can you actually?
No, it's loading in. It's loading in.
My internet's not great. Okay, well, if it works later, it might. Yeah, who knows? Okay. Anyway, sorry. As I was saying, basically this week there's not that much extra in terms of content. It's only moment amp, and then you'll see later at the end biaxial bending. But those are minor steps, right? The main problem is that beam column design is a very step-by-step process. So if you've been up to date the rest of the term, you're gonna find this week pretty easy. But what tends to happen is most people aren't up to date on the course, right? So they see this topic and they're like, fuck, they're super overwhelmed and whatever, because it's the compression topic, including gamma method from week 3, and flexure combined, basically. Okay, so I just put a disclaimer here because Prash's notes for this week in particular, I basically just copy pasted because there's nothing I would improve from it. Essentially, like, that was so good. I've been working off of his notes for like most of the weeks, but I've kind of just, it's kind of like on Turnitin, right? If you change it a bit and like, you know, you build on the source, it's not like really plagiarism, right? This one I straight up plagiarized. I don't think the camera's gonna work, so I'm gonna give up for now. But yeah. So beam columns, right? Take a look at this one, for example, right? So we're talking about frame systems here, essentially, because, you know, you have columns and you have beams, and we're designing these. We're designing the columns which are attached to beams. So we're gonna focus, for column design, we focus on combined axial forces and bending moments. My light keeps turning off. And so basically, I want to start by talking about the way that moment, like bending moment, ends up in columns, right? And we're talking about columns with rigid connections, as you can see here. So primary means, this is called first order. So this is getting like a little bit down to like first principles of structural engineering, but like, don't be too scared off by this. We're just basically primary means or first order moments are just from the bending moments that you solve in 1300, right? So probably everything that you've seen so far in terms of like calculating moments on a frame, whether it's from 1300 or like 233, has been from primary moments, essentially, right? And yeah, when I say this point here, beams transform moments into the columns through stiff connections, right? Or also called moment connections. The idea is that a lot of loading on a structure comes from like gravity loads, right? Vertical loads, they usually fall on the beams or slabs and then into beams. And then from the beams, they transfer onto the columns, right? You don't really, there's not usually like a big fat point load that just sits onto the column. Usually what happens is that, you know, this uniformly distributed load works its way into the column, right? And then because it's not pinned, because it's rigid, right? You can imagine the bending moment diagram. Let's just ignore that for a second, right? It would look something like this, right? It might look different. Okay, maybe I'll pin these just because it's simpler. Yeah, so it might look something like that. So again, everything comes from the gravity loads, and then yeah, and then that's how you end up with these moments here in the corner, because the moment is continuous around the corner. Any questions on that so far, guys?
No.
Fantastic. The next way that moments end up in columns, right? Let's just forget the distributed load at the top for a second, is from lateral wind loads, right? So when you get a wind load, you get shear forces, right? So I'll just pretend those out here again. You get shear forces, so then you start getting, which way do I want to draw it? shear force would then start looking like this. No, that doesn't look right. It looks like that, you know, that's the shear force. And then you get your bending moment. Like, not like that. It's like that, I think. Is that right? Okay, I've done something wrong. But basically, yeah, point is, yeah, wind will induce moments in columns as well. Right. Okay. The next way is through secondary means, okay? So this is also called the P delta effect. P delta. And this is basically saying that when you apply an axial load, let's just focus on this right here. When you apply an axial load into a column, it will, it could potentially cause an offset. Like it could be potentially offset and then cause this kind of bending in the column, which causes it to be more offset, like the point load is more offset. And then it just keeps bending due to these kind of like imperfections in like eccentricity of the force, right? At that distance there, that's called delta. So when you see P, it's referring to a load, right? In this case, it was from a distributed load, and then half of that distributed load works its way into that column, half of it works its way into that column. What I've described as P there is whatever half of that distributed load was, right? And then delta refers to that kind of eccentricity. So it will work slightly differently for sway frames and brace frames. So this would really help if I could share my camera. Let's see if I can work. Okay, what if it works on my other device? Okay, it works on this one. Okay, you guys can see me hopefully now, right? What the fuck? Okay, so let me just check this works on the recording as well. Okay.
We can see you.
You can see me?
Yeah, we can.
Okay, fantastic. So pretend this is a frame, right? My fingers, where this bottom finger is the ground, right? And the other ones represent the two columns and the beam at the top, right? So if there is a horizontal force, like a wind or something, that knocks this frame to the side, it's going to sway like that, right? Because it's not braced, essentially. It's prone to this kind of behavior, essentially, right? Conversely, right, imagine diagonally we had braces, so like this pen, and let's see if I can do this. Probably not. Okay, imagine it's cross-braced, right? So these act in tension and pin corner to corner, and it works for the other corner as well. Now, if there's a wind load, my fingers are locked, basically. So it's called braced. It's called a brace system. I didn't really show the video or whatever. Okay. Okay, so that's that demonstration. So, okay, let's go back to this. So, essentially, there's two types of P deltas. There's P big delta, right, which is triangle, and then there's P little delta. So when we refer to P big delta, that's talking about the sway frame, essentially. And we call this eccentricity caused by global circumstances, right? Now, small delta is slightly different because when you have a braced frame, I should probably draw this brace. When you have a braced frame like that, you see the delta a little bit differently. So before it did this, right? And that was delta there. Now delta is from wherever it buckles the most. So now it's caused by, like say this point doesn't move left or right. That eccentricity is caused by the buckling of that column itself, right? So that's P little delta. Anyway, point is, these are both ways that secondary moments can be introduced into like a column, right, in a frame system. So this is called local circumstances. Anyway, point is, this is all context. But does this kind of make sense to you guys? Okay, I don't want to keep going until this makes sense.
I think in the context that you did tell us, yeah, it does make sense.
Okay, fantastic. That brings us to AS4100. So AS4100 handles P delta interestingly, and it's specific to the way that they analyze steel. Now, I think this is handled slightly differently for concrete or maybe other materials, but this is the way that it's presented in AS4100. So it's saying instead of summing your primary and secondary moments like you would do in like a first principles based approach, instead you get your primary moments, which again is just from bending moment diagrams. You don't do anything differently from how you've been solving for moments, right? You have to find this moment amp factor, right? And then it's interesting because you know how I said P delta, all that stuff? This is technically delta, but now we're kind of multiplying it, so it's M times delta. So it's a little bit differently because this delta is either delta S or delta B. Don't think of this like displacement exactly. It's just a moment amplification factor. So delta S here stands for sway frames. Delta B stands for brace frames, right? So for brace systems, right, here's the way it works. If you don't have any compression, delta B is 1. And that's just because, going back to thinking about the finger example, right? If you have a braced frame, I know you guys can't see the camera, right? But if you have a braced frame, and it cannot move due to like lateral loading and whatever, like there's eccentricities causing your P delta effects, right? If you don't have Euler buckling, right, which is no compression, so if you don't have any compression, you can't have that kind of when I say Euler buckling, do you guys know what I mean? It's the global buckling effects, right? If you don't have any global buckling effects, right, you don't have to amplify your moments because they just behave the way that you'd expect them to behave. But if you do have compressive behavior, what happens is the Euler buckling effects will amplify, or they could amplify how bad your moment is on your column. Hopefully that makes sense. So that's what we're calculating using this formula, right? I think I could be delusional, right? But I think this like all is quite clear in terms of the theory. Are you guys following along? Or?
Yeah.
Okay, fantastic. Now where it becomes unclear is the formulas start to get a little bit tricky because on a conceptual level, I don't think it's too bad. We're following this formula, right, which has a couple of things you haven't seen before. Cm is a constant, and NOMB, nom, is another constant. We'll talk about those. Cm is the factor for unequal moments, right? Actually, I shouldn't highlight like there. It's like just that, right? And it's a function of beta m. Beta m is your ratio of smaller to larger bending moments at the end of the column. Now, it is only this definition if you don't have transverse loads. So what I'm talking about is if you have wind loads, you have to use a different formula. It's in the code, but you can't use this ratio method. Sorry, I shouldn't say you use a different formula. You have to use the figures 4.4.2.2a/b to figure it out. It's very similar to, do you guys remember alpha m? Maybe you don't, because it's a part of the flexure topic, but you didn't really need to use it in your assignment, so some of you guys might not be super familiar with that. But it's basically like looking at graphs and trying to decode a puzzle. In a very similar way, trying to deal with finding beta m is like that, except you only need to do that puzzle shit if you have transverse like loads like wind loading and things like that. Anyway, point is, if you have kind of more standard, so no transverse loading, the bending moment diagram might look like this or something, like any of these shapes instead. So they'd be linear essentially, right? Yeah, I just provide some examples, but it's the negative of the smallest moment to the largest moment, right? So if they're flipped on different sides like this, it's negative negative over the bigger one, right? And then it just becomes 0.9, etc., right? And if your smallest moment is 0, if it's like pinned, for example, then beta m is 0. And then beta m feeds into cm, basically. Now nom, right? Later we're going to see n or ms, right? Noms. These are different, and it's based on this last letter, right? B stands for braced, and S stands for sway, like for sway frames, right? So this is essentially your elastic buckling load, right? I think way back in like week 2 or something, I talked about what is the theoretical elastic buckling load, or like Euler's buckling load, or something like that. I'm like, oh, don't worry, it's not going to be in the course. Here it is. So this is kind of like in your assignment. Do you remember the reference buckling moment? MO?
Yeah.
The reference buckling moment is essentially the buckling moment for lateral torsional buckling, which is something to do with bending, right? Something to do with flexure. This is the equivalent, but for axial Euler buckling, right? Pure compression buckling. And the formula is way simpler. Now the problem is we're going to have to use gamma method to find KE. We'll get to that, but before we do, does anyone have any questions? I'm going to assume that's a no. So, cool. Next we'll go to sway structures. So, just imagine, right, you can see my webcam, and then, like, I have my fingers out again, right? Sway structures are the ones which don't have the cross bracing and can sway, essentially, right? So if you imagine that, like, I might just draw it actually. If you imagine a frame with multiple stories like this, multiple columns, and we want to find, for example, how much this column is swaying or how much this column is swaying. Well, essentially we're saying that all of these columns actually have their moment amplified the same amount because of the sway. We're basically accounting for all of the columns in a story for this formula. So whenever you have to find, like, for example, column 1 or something like that there, you have to think about doing the calculations for all of the columns in the story. Does that make sense? A lot of the time it's copy pasted, but yeah, it's still good to know, basically.
I don't understand. You just do it 3 times, or you gotta like merge the forces together?
You'll see below. It's a sum of, basically.
Oh, a sum of. Okay.
Yeah. Okay, but what you do have to collect first is the elastic buckling load for all of the columns, right? In that, so that elastic buckling load, that elastic buckling load, that elastic buckling load, etc. Now the thing is, a lot of the time these columns are going to be the same in terms of the member that is chosen. For example, if this is like a 200 UC, this is probably going to be a 200 UC. So they're not really going to screw with I, right? Unless they're evil, but they're not going to do that. What might change is L. For example, L might change because the length of the columns might be different. Something like that, right?
Sorry, just to clarify, is it the spacing between the columns, or is it the length of the actual columns?
It's the length of the
L
actual
term.
column. Yeah. I might just quickly talk about Euler buckling again, just so everyone kind of can visualize it. So if we have a column and we apply an axial load, like at the top, for example, what's going to happen is this column might buckle like that in a C shape, right? So this is if it's pinned on both ends, and there's no stiffness otherwise. So when we refer to L, we're talking about that, basically, the length of the member, because the longer it is, right, the less it's going to take to, the less force it's going to take to cause that buckling, right? So imagine, it's a good example. Imagine like a stick that's the length of a pen, right, and you push down on it, right? It's going to be pretty stiff, right? It's not really going to buckle so much. But imagine doing the same thing, but with a stick the length of, I don't know, the size of your room, right? It's going to not take very much to cause that to break through buckling. Okay, the other thing is that the columns might be loaded. This is more likely that they're going to be loaded differently. So whatever forces are going to be here, here, and here. Oh, sorry, I should say whatever axial forces you end up finding here might be different just because of the loading on top. So you have to collect that for all of your columns in the story. Now this is where I get to the fact that we sum it. So if you have 3 columns like I drew here in a story, you will end up having, you know, 1 number over L plus 1 number over L plus 1 number over L, and then, you know, same thing basically. So it end up looking like this. So that's why you have to collect noms and n star for all the ones above. Okay. So once you get whatever that number is, it'll come out as some constant. We chuck it in here essentially, right? And that's how you're gonna get your moment amp, right? Okay. Does anyone have any questions?
Sorry, what was noms again?
Oh yeah. So actually, noms and nom are the same. Unless I did something wrong with writing them down and they're actually different, but I'm like 99% sure they're the same. All that changes is that one is in reference to braced, for braced columns, and one is in reference to sway columns.
Okay.
For braced, you're only considering a single column, right? So for braced, we only care about, okay, what's the buckling on that column? Like, what happens in this column doesn't affect the moment amplification in the column on the left, right? Whereas for sway, it does.
Oh, okay.
Yeah.
Yeah, okay, sweet.
Does anyone have
One last question.
Yeah,
just one last question.
Go on.
The one on the lambda ns. Can't you just cancel out the what's it called, the 1 over L terms on the top and bottom? So you just get the sum of n OMS over n star.
I think you'll find that is not how the algebra works.
Okay, good. I was just wondering if you could.
Yeah. I think I've had that thought as well before, but no, I think it won't let you do that. Just because the plus signs will kind of prevent that from mixing, you know.
Oh, good.
Yeah. Okay. So, we'll go into the step-by-step of beam column design. Now, I'll give you the short version and I'll give you the long version after that, okay? So here's the short version. In steps 1 to 3, we'll talk about, you know, analysis, but this is mostly just implied, implied is it the right word? It's assumed that you kind of know how to get bending moment diagrams. axial force diagrams, right? The next step is moment amplification. That's just what I ran through, right? Somewhere along the way, that S disappeared. Yeah, so identify whether you've got a braced system or a sway system, right? And then use the formula accordingly to amplify M. So whatever you get for MX star and MY star, you gotta multiply by these, right? So what I mean, by the way, MX star, MY star, right? If you find that you have forces going this way, let's say, your bending moment will go that way, right? Let's say that's X. If you have forces going this way, your bending moments will go that way, behind. That's MY star. That's based on this assumption that, you know, x-axis, y-axis. So, yeah. So, I didn't really draw that very well, but basically, whatever the major direction was, okay, maybe I'll draw it like this, like an I-beam, right? I-beams like that, for example. Yeah, does that make sense?
Yeah, I think it's reference to like the first assignment. They did something similar with the YY and like that.
Yeah, exactly. But my point is, you're gonna have to say this is braced. You're gonna have to multiply these by the same constant, which is delta. Oops. Okay. Next, gamma method for effective length. Now I'll go over that properly when we get to that step. But whatever was in week 3, I don't think a lot of people took the time to learn it, which is fair enough because it wasn't really required for your assignment. But don't worry, we'll cover it. Compression design. This one was covered in your first assignment, so this will be a bit more familiar. You have to find the slenderness ratio, the modified slenderness ratio. You find alpha B, and then that will let you find alpha C. You know, you find NS, you find NC, you check the capacity, all those things, right? For flexural design, this is MS was probably pretty familiar to you guys. A lot of the time, it's going to be a one steel shape. It's probably not going to be a custom shape for your finals. So it's just a matter of finding ZE and FY on one steel. Then we have to worry about restraints. Is this restrained against lateral torsional buckling? MB. Yeah. That's like, it's like alpha M. Alpha S value, and then that's multiplied by MS, and it can't be more than MS either. And then you check the capacity, so on and so forth. And then we also have section yielding and member buckling checks for combined axial and moment. Yeah, as you can imagine, if it's getting like kind of attacked in two directions, if it's getting bending moment on it as well as the buckling, it's going to have a weakened kind of capacity, and then we have to check whether then that will satisfy given various loading, M star, X, M, Y, X, etc. Right? Cool. Makes sense?
Yep.
Now I think on paper this seems like okay. I've managed to fit the TLDR version on one page, but a lot of the time, if you get given one page of notes like this, and you walk into your final exam, you're not gonna know what the fuck to do, right? Like, and if you are given this as like a little reminder, and you do know how to solve it, you're at a point where you're going to probably get a HD, right? A lot of the time, the difficulty comes in each individual step because there's quite a few sub-steps in it, right? So that's what I'll run through next. Yeah, so here I've just put down dead load, live load and dead load, and wind as the combos. But yeah, load combinations. In some of the practice questions, they straight up give you like, okay, here's a frame, la-di-da. And then they might give you another one. It's like, oh, here's the axial force diagram, and then it just shows you like how much compression or whatever is here, probably bigger, and here, and then like here or something like that, and then bending moment diagram. I'll draw the frame again, and then it'll give you like different bending, kind of like the little example I showed you above. I don't know what these would look like. I'm just guessing. Whatever, right? Oh, not that. Like that. Yeah. So sometimes you don't need to do the load combos because they'll just give you these, right? And sometimes you don't need to solve it yourself. They'll just give you these. Basically, if you know what these things are pretty well, then you can just kind of deduce what they want from you. Sometimes it's not about like strictly following these steps as much as using this as like a guideline, I guess, and trying to fill in the blanks yourself. Okay, column loading. So this is for axial forces, right? I'll just give you a little example, right? So actually, wait, let's just talk about this little analogy, right? So say you have like 3 kids and they're like shoulder riding, whatever, and each kid weighs 30 kilos, right? How much weight does the top kid, like does the kid at the top experience, right?
Just 30 kilos, not?
Yep. What about the second kid? How much
60.
weight is this? Yeah, exactly. 60 kilos. What about the bottom kid?
90?
Exactly. So what this is, what I'm trying to demonstrate, right? I know this is incredibly simple, is that the way that you work out the loads on a column, right? Say I didn't write any of this. We want to find how much axial force is here and how much axial force is here, right? How would you do that? First, you start from the top. So this is like the same as looking at the kid on the top, right? Okay, that's the roof loading. Half of it will go here, half of it will go here, right? So you find out, so for example, the G that goes into the column on the left is 12 kilonewtons per meter times, this whole thing's 6 meters, so 3 meters of that goes on the left, right? That goes into that column there, and you work it out for Q and you work it out for G, and then you split both ways. Then what goes into this column? Well, like the analogy with the kids piggybacking, right? Everything from above stacks on, and then you add it on, and so on and so forth, right? So that's how you would find it, like N star C, basically, at those columns, column 1 and 2. That's just called a load rundown, basically. Before I move on, does that make sense? Yep. Fantastic. Okay, so the third step is we want to note down all the important values from one steel. This is going to help us for gamma method. It's going to help us for a bunch of things, right? We're going to collect quite a bit for columns. This will help us for MS and reference buckling moment. Pretty much everything else will help us for compression as well as some parts of flexure as well. We only care about the stiffness of the beam for gamma method. And beams, so if you imagine like beams connected to columns, right? Let me just draw this in 3D. Right, so that's a column, perspective view. If a beam's connected to it, you can bet that the beam is orientated on its major axis, like that. Because it would be a bit stupid if the beam was sideways. Now I've seen beams sideways before actually. For some reason I saw one sideways in like a bouldering gym. I don't know why, because I've heard that it's for like wind loading. It's better at resisting wind loading like that. But it was like on the ground floor of a bouldering gym, so I have no idea. Yeah. Okay. But point is, assume that the beams are orientated on its major axis, not its minor axis, sideways. For columns, they could be either, because if we're looking at a warehouse, for example, I'm just going to draw a really small warehouse. So this is top-down view. Those are the columns. These are the rafters that span in between them, with a little ridge at the top. For these columns, it can essentially buckle this way, right? Imagine like axial forces going on it, and then you see it kind of bowing out this way, or it can go this way in the minor axis. Just depends on where your restraints are against Euler buckling. So we need both IX and IY basically, because it can buckle in either direction. Cool. So now there's a refresher on gamma method, right? So this, I covered this a little bit more thoroughly in my week 3 app, I want to say, but I'll just talk about it briefly here. We're trying to find what is the stiffness of a column, right? So it might help to show you guys the simplified version, right? The way that I like to describe it, so this is idealized method, so this is different to gamma method, is based on the supports, and it's based on whether you have a brace member or a sway member, essentially, right? How I like to think of it is, how big is this C shape relative to the length of our column, right? We say the C shape takes up 100% of the column. Okay, what about this one? So it's pinned on the top side and rigid on the bottom side, right? It takes up roughly 85% of that C, like the C shape is 85% of the length. Okay, what if it's rigid on both sides? Okay, then it's 70%, right? That's the case for a brace member. For a sway member, we're saying, okay, even if it's fixed on both sides, right, you're gonna have that P delta effect, and the C shape ends up being 120% of the length. Even worse, if you have these loading cases, right, like either the top or the bottom pinned, 220% of the length, right? It's pretty bad, because the longer it is, the more likely it is to buckle. Think back to the example I gave with the stick. You know, if you have a stick the length of your entire room and you push on it, it's very likely to buckle, right? Oh shit, I drew that on my proper notes. Let's undo all that shit. Cool. So what we looked at, you know, the thing that said like 80% or 85%, 70%, all that, that is KE. KE is the modifying factor for your length. So effective length is KE times your length, right? And we have a version for the X direction. We have a version for the Y direction. This applies to only Euler buckling and compression, right? But we still have to find it. So how do you find KE? We use the gamma method. So say you have a frame like this. We're interested in finding the stiffness of this column. What do we have to consider? We have to consider the top node and the bottom node. The bottom node is going to have a value called gamma B, and the top node is going to have a value called gamma T. to describe their relative stiffness, right? So for gamma B, if it's the footing of a building, like how I've drawn here, it's very simple, right? Gamma B is 0.6 if it's a rigid footing, like how I've drawn here, right? It's 10 if it's pinned. This is a hard rule that's written into AS 4100. So what I mean by it being pinned is if this was pinned, for example, right, like that. If we were analyzing, that column, we just straight up say, okay, the bottom is 10 for the value for gamma B, right? But if we analyze the column which I highlighted on the left here, gamma B would be 0.6 because it's rigid. Okay, that brings us to gamma T, which is the top node. Now the top node has a little bit more going on because it's attached to another beam. Oh, sorry, not another beam. It's attached to a column. And not only that, it has a beam coming up of it, right? So we consider the stiffness of the column above the column that we care about, as well as the beams attached to it. And in this case, we only have one beam that we care about attached to it. But what happens if we were analyzing, let's shift the attention back to this middle column, right? If we were analyzing what was gamma T here, we would have two columns and two beams to analyze, essentially, right? And in terms of the beams, and so that brings us to this equation, right? So essentially the top of this fraction is going to be the sum of the columns moment of inertia divided by its length, right? Whereas the bottom is going to be beta E, which is some constant, which I'll talk about in a second, multiplied by the stiffness of the beam over the length of the beam, right? So we care about this length, this length, this length, and this length here. It's for gamma method. For our beams, we care about their moment of inertia only in the x direction, but for the columns, it will either be Ix or Iy, and it depends on our orientation. So, do I have a good example here? I don't really have a good example here. Let's take this for example, right? Say we were analyzing an elevation this way. Is that a good example? No, this way. We're looking at this portal frame, right? I'm gonna have to destroy a lot of this to prove this point. That's our columns and that's our roof, right? Our rafters. Let's just draw it flat. And essentially, based on these columns orientated in plan view, are we going to see the flange first or the web, basically? It's kind of a trick question. Yeah, but you'll see the web, and then you'll see the two tiny flanges on the sides, right? Like little plates. So imagine that red part's the web, then this would be like what the flange looks like, right? Something like that. When we analyze a frame like this and analyze it with gamma method, you have to think of it like it's tipping over, right? So imagine this way, right? And that's the axis which the columns that we analyze are going to be bending about, okay? So I'm going to draw this like this. Those are the flanges, that's the web, right? Of that column. I've just kind of flipped it so the cross section's like flipped up, right? What happens is it is going to be bending about this axis, right? Because we're analyzing it as if the frame is tipping over like that. Does that kind of make sense?
Yes.
Yeah, it does make sense.
Okay, so does that make it major or minor axis bending for this specific I column or universal column?
Minor?
Incorrect.
Mm.
So when you see this way, and then I drew the dotted line the same way, you would probably recognize them more as major axis bending, right?
Yeah.
Do you know what I mean? So if it's bending along that axis, if wind is causing it to go like that, I say wind, but this is like an arbitrary force or whatever. This is just how you do gamma method stiffness, right? Yeah. Point is, it's bending about that XX axis. It just looks a little funny because we're doing a sideways kind of bending.
Oh, yeah.
So, in that case, which I just showed there, that's when you would plug in IX to the column formula. Oh, sorry, to the gamma method formula, right? For gamma top. Anyway, yeah. One more thing I want to talk about is beta E. So that's a constant for the beams. Now, if the near end, so again, we're still analyzing this column, for example. If the near end is pinned, right, beta E is 0, which means there's no contribution of stiffness from that beam. That's essentially what it's saying. If the far end is pinned or it's rigid, we have different constants for it, and it's based on whether it's braced, whether it's sway, and what the far end's doing. But yeah, basically if the close end is pinned, there's no contribution of stiffness. Okay, any questions? Let's gamma method. By the way, I'm not going to run through an example today, but on Friday, I'll be going through an example of beam columns. The rest is pretty similar to what you've seen in the rest of the course. So yeah, you use the gamma numbers that you get for both ends. So say you get 0.6, right, for the bottom, and then say you get, I don't know, 1 or something here, 1.2, I don't know. Then this line is 0.75, so your KE factor is 0.75, for example. Yeah, anyway, so that's gamma method. Next, you have to amplify the bending moments. We've talked about this. This is just the moment mod factor. So you just follow through moment mod. And then next we find the modified slenderness ratio. So now we're moving into the territory of we're trying to find NC, which is the compressive, the beam's capacity in Euler buckling, or in member buckling, I guess you can call it. So that's all from assignment 1 kind of thing. Yeah, I've just provided, like, in the step-by-step, I've also just provided everything you need, so you don't really need to go back and see the other notes. You can kind of just work it out from looking at this. If it's your first time seeing it, okay, yeah, maybe you can go back and like look at it in more detail, but if you just need it like as a cheat sheet, then I've tried to lay out this week's notes kind of like that. And then you're following this graph, so, you know, I got the moment, like the modified slenderness ratio, I got as 100, for example. I go up to the line, which, let's say I got 0 for alpha B. Okay, my alpha C value is 0.55, right? So remember, NC is NS times alpha C, which means that we lost 45%, right? We lost 45% of our capacity because of Euler buckling, right? So if this was 100 kilonewtons was how much it could take before, now it can only take 55 kilonewtons. And then we do our check. Okay, and then this should look relatively familiar because you just recently did the flexural assignment. You find the nominal section capacity. Now, this is going to be a little bit weird because you probably haven't seen the Y version before. But as you can imagine, you need to check for both here because, oh, well, rather, yeah, I'll just say yes. So, yeah, you'll need to check for both. And then we need to check whether the member has full lateral restraint. So, whether it's going to laterally torsionally buckle, you have to see whether the critical flange is sufficiently restrained. If not, we have to calculate MBX basically, using your effective lengths, things like that. So yeah, I've included what it takes to find LE for, now this is a different LE, this is the LE for lateral torsional buckling. Yeah. This one's quite important, top flange loading. Yeah, I don't really have time to run through all this in detail at the moment, but anything I don't cover properly today, I'll try to do on Friday, basically. Reference buckling moment, you guys are super familiar with this shit, the monosymmetric eye sections, right? A lot of the time we'll be doing one of these for this part of the course. So one of the less demonic formulas, basically. Yeah, so remember from the things that we grabbed from one steel, that included the torsional constant, the warping constant, and the minor moment of inertia. Yeah. You find alpha S, so that's easy once you've gotten reference buckling moment. So I would, in your exam, if you're given a beam column question, I would just have alpha M as 1, so that's pretty conservative, assuming it's not a cantilever. Or you can use the next page and spend a bunch of time trying to figure it out like a puzzle. You can, yeah, sure. I'll leave it at that. You can do it if you want. Okay, and then next is member bending capacity. So, yeah, actually I'm not going to draw a diagram again. You guys kind of know what I'm talking about. We have a bending moment, right, which can potentially happen in the x-axis axis and the y or the y axis, right? So we have to find how strong the entire member is against flexure in both directions. Okay, now it gets cooked, right? Because now shit's just gonna start sounding the same. I'm just gonna start speaking like in fucking Greek, right? So I didn't just say Greek randomly. I meant it because like the symbols and shit. But yeah. So the reduced section moment capacity is because of combined action with axial forces, right? So if you have axial forces acting on your member as well as flexure, then you're gonna have to use this formula basically, right, to reduce it. So that was the section checks, right? We had a reduced section capacity, right? So let me just visualize this for you. Remember, for moments, let's just take your assignment for example, right? You kind of had a really fat bottom flange. Say you had a really thin web or something like that. And the top flange is like, okay, right? Remember that your section slenderness is governed by the weakest element. Should I say min? I think it's max. The max slenderness ratio, right? And it's to do with like yield limits and things like that as well. But say that web is incredibly thin, right? So it's definitely going to be the one that governs. That one is causing the member to be weaker against lateral torsional buckling. Like this might buckle and flexure or whatever, right? Like locally. Remember, that's what your section capacity is. For member capacity, here's where it gets cooked, right? Because lateral torsional buckling is where you have, let's say that's an I-beam. as you load this, right, you're gonna have your I-beam. Yeah, I'm gonna draw like this. Here's where it was. Here's where it will be. So as you load it, it's going to go down because it's going to deflect vertically, and then it's also going to want to buckle in the compressive zone while pulling in the tensile zone, right? So you're going to have this spin, which causes, so it's going to want to move out when it's compressed, or pull together in the middle where it's being pulled in tension like a rope, and so it's going to cause this torsion, right? That's lateral torsional buckling. And so, yeah, essentially, here's where you're gonna have to. Shit. I'm pretty sure I wrote these formulas right, but now I'm starting to doubt myself. Yes, yeah, it was a B. Fuck. I'm starting to doubt myself now. Okay, I'll make a correction in editing if this is wrong, but yeah, there's these formulas essentially, and it's to do with the member capacity essentially, right? Here we have the member capacity for compression. But yeah, so yeah, we follow this like kind of flow chart, right? So is the member bending about the x-x axis, right? So back to this example here, right? I'm gonna copy that and bring it all the way down. Is this member bending about the x-x axis in plane, right? So in plane means moving in on the page. Out of plane means in and out of the page, right? You can imagine this coming towards you or something like that, or away from you, this whole frame, like that, right? It's kind of trippy, but that's out of plane. So in plane, is it bending against the x-x axis? Yes. So check the in-plane capacity requirements using this formula for x-x bending. Is there sufficient restraint to prevent lateral torsion and buckling? Yes, no. If no, it can also buckle out of plane. So it's hard to draw lateral torsion or buckling in 3D. Just like that. And then also it's out of plane. So that's pushing away, I guess, from the page, while also laterally torsionally buckling. That's like one of the flanges. Yeah, so if it's not restrained, do that. Whether you do yes or no for that, you go to check 3, right? Is the beam column under biaxial bending? If it's not, you're done. If it is, last formula. Just top things off. So yeah, this is like a Prash formula basically. This is from first principles, but it's not in AS 4100. But yeah, he always recommended when he taught me, just do it. Yeah, that's basically it. That's bending in and out of the page, as well as on the page. Okay, any questions?
Is the MS and MY, is there a difference in how you calculate that? I'm a bit confused. I mean, sorry, the MSX and the MSY.
So, MSX, MSY. We use basically a different value for your elastic section modulus. So that's your elastic section modulus, right?
Yep.
So, let's just take an I-beam for example, right? I'm gonna draw it very deep because that's what an I-beam looks like, right? So the idea is, let's just focus on Z, right? first yield looks like this, right? And that's your neutral axis. That's when it just hits first yield, correct?
Yeah.
If you remember from your assignment, you can do Z is equal to Ix over Y hat, whatever.
Yeah.
Okay. Let's take the exact same I-beam, but flip it on its side now.
Oh, okay.
Oops. And now, we also have first yield, but we had to calculate Z differently because we had to use this formula instead. So that is ZY and that is ZX. So you've been calculating ZX the entire time. You just didn't call it ZX.
Okay.
Oh, sorry, you were calculating MSX and ZEX. You just didn't call it that because for beams it's kind of, it'd be stupid to orientate the beam like on its minor axis, right? But for columns, since we're dealing with columns now, like it could bend either way. Do you know what I mean? Oh, sorry, I wrote this part wrong before. This should be Y. So that's for first yield. Oh, sorry, wait, were you gonna ask another question?
Oh no, that's all. Thank you.
Yep, all good. So that's for first yield. A better representation for ZE looks more like that, right? And it's just a function of, you can look back at the notes, it's a function of slenderness ratio and shit like that. But it's basically a number that's in between your S value and your Z value. So ZE would look a bit more like that. Some of it's plasticized, essentially.
But we use the triangles to calculate it.
No, you just use one steel. Because you're not going to have a custom shape anymore after your assignment, probably.
Oh, so in the exam, you mean?
Yeah. In the exam, I guarantee you he'll give you something from one steel.
Oh yeah, and yep, they have the ZE and ZX
Yep,
stuff.
it's straight up listed on there for every I-beam and like whatever I column.
Okay.
But yeah, as you can imagine, this value ZEX is going to be way higher than ZEY for an I-beam, because, or even an I-column, because I-beams are just so much weaker in the minor axis. Cool. Any other questions?
Nope. All good.
Nope. Okay, I'm gonna stop recording. Thank you guys.